The last way we might be given a surface is when the surface is given as a graph. So we have one variable as a function of the other two. Then when we look at the inputs and the outputs together, then that creates a surface, because in this case every point in the xy plane has a corresponding height z, and so that creates a surface when you look at the graph. So what's the correct conversion factor in that case? Now we've already seen that if you have a parametric surface, so if you have your location as a function of u and v, then the conversion factor is going to be the length of r sub u cross r sub v. And when you have the surface as a level set, so if you have some function where x, y, and z, some function of x, y, and z that's set equal to constant, then you've got one constraint on 3 dimensions, so you're left with some 2-dimensional surface, then the correct conversion factor is going to be the gradient of f divided by, or the length of the gradient of f divided by the absolute value of the gradient of f dotted with the projection direction. So that's our conversion factor. In this case, now we want to figure out what's the conversion factor of z as a function of x and y. Now we can actually do that in two ways. One way is to say, well, when one variable is a function of the others, then there's always an easy parameterization that's available. You just let the two input variables be themselves, and then the output variable is determined by this function little f, and so you get this parameterization. Right? Then to find the conversion factor, you can just apply this formula. Let's see, the derivative of r with respect to the first parameter is 1. Let's see, derivative of y with respect to x is 0. And the derivative of this would be the partial of little f with respect to x. And the partial of our parameterization with respect to the second parameter y. Let's see, the derivative of x with respect to y is 0, the derivative of y with respect to y is 1, and the derivative of this with respect to y is f sub y. And we need to compute the cross product, so we'll just put them quickly into a little matrix here. We'll get r sub x cross r sub y is going to be, let's see, I times 0 minus f sub x, and j times f sub x times 0 minus f sub y, and k times 1 minus 0. So that's minus f sub y. So the correct conversion factor, if you think of it this way, is the length of r sub x cross r sub y, which would be, let's see, the length of this would be the partial with respect to x squared plus the partial with respect to y squared plus 1. The other way to think about it is if z equals f of xy, then you could subtract this over, and now you have a function of 3 variables, x, y, and z, that's set equal to 0, so this is actually giving you a level set. So call this guy capital F of x, y, and z, right? Depends on x, y, because those go into little f, and then there's the z dependence right there. Let's calculate the gradient of this function capital F. Well, to find the gradient, you take the partial with respect to x first. The partial of this with respect to x is 0. The partial of f with respect to x would just be, we just get negative f sub x. And let's see, the partial with respect to y is negative f sub y. And the partial of this with respect to z, this doesn't depend on z, so its derivative with respect to z is 0, but the derivative of that with respect to 0 is, with respect to z is 1. So, and also, if we have some surface, right, so we've got x, y, and z is a function of x and y, then the natural projection direction would be k, right? Because then we could project, this is a function, we could project right down onto the xy plane, and every point here would correspond to a point there. So when we want to do the gradient of f dot with the projection direction, the natural projection direction is k, and if you do k, which is 0, 0, 1, dotted with minus f sub x, minus f sub y, and 1, you just get 1. So the conversion factor would be the length of the gradient of capital F over the absolute value of the gradient of f dotted with the projection direction. It's just going to be the length of this vector, which is the square root of f sub x squared plus the square root of f sub y squared plus 1, all divided by 1, which gives us the exact same conversion factor. So this case where z is a function of x and y, you can think of it either way. Either do it as a parameterization, right? You get this conversion factor, or rewrite it as a function set equal to 0, so that it's as a level set. Whatever way, whatever formula you apply, you're going to get this same conversion factor. Okay, let's look at an example. So we've got here, this specifies a hemisphere. Notice that if you squared both sides, you'd have z squared equals 4 minus x squared minus y squared, or x squared plus y squared plus z squared equals 4. So that's a sphere, but what's been done here is we've solved for z and then taken only the positive square roots. So this is just the upper part of the hemisphere. Okay, so we have it. We have z is a function of x and y. So we can just look at any point in the domain here, and the domain of this function, we just have to have 4 minus x squared minus y squared has to be greater than 0, and so the domain is really this disk inside the circle of, so the boundary here is the circle x squared plus y squared equals 4, and we just have to be inside that disk. So that's our region of integration. We're going to integrate over that region, but when we have a little patch down here in the shadow, what is the size of the corresponding patch up above? We just need, that's what we need the conversion factor for, and we saw before that the conversion factor to change areas in this flat region in the coordinate plane to area on the surface in 3 dimensions is going to be f sub x squared plus f sub y squared plus 1. And in our case, f of xy is this function, 4 minus x squared minus y squared to the 1/2. So f sub x is going to be 1/2 of 4 minus x squared minus y squared to the negative 1/2 times the derivative of what's inside, which is negative 2x. Let's see, those 2's are going to cancel. Because of the symmetry in the problem, x and y can be interchanged. So if I take f sub y, x and y can be interchanged. So I can just do 4 minus x squared minus y squared to the negative 1/2 times y. It's just the same procedure, right? Okay, so so we have basically negative x over some square root, and oops, there's a negative there, and negative y over some square root. So to calculate this in our conversion factor, f sub x squared is going to be x squared over, if you square this square root, you just get 4 minus x squared minus y squared plus f sub y squared. There's a y up top, so that gets squared and becomes y squared. There's a square root downstairs that gets squared and becomes 4 minus x squared minus y squared, and then plus 1 from here. If I go ahead and get a common denominator of 4 minus x squared minus y squared, I have x squared plus y squared, and this, to get the common denominator of 4 minus x squared minus y squared, has to be multiplied top and bottom by that. So 4 minus x squared minus y squared all over 4 minus x squared minus y squared. Okay, and let's see. That all adds up. We've got 4 over 4 minus x squared minus y squared, or if I use the fact that the root of the quotient is the quotient of the roots, the square root of the numerator is 2, right? And then we over the square root of 4 minus x squared minus y squared. So to find the area, we've got to go along the surface, just adding up 1 times a little patch of surface. But we can see that corresponds to going throughout this region. Let's see, we need to, if we look down on this region in the xy plane, just looking at the domain for that surface there, we have a circle of radius 2. So one way to set up the bounds would be to say, okay, if this is a circle of radius 2, x goes from negative 2 to 2, and y goes from, just solve this equation for y goes from the negative square root of 4 minus x squared up to the positive square root of 4 minus x squared. So we get these bounds. x from negative 2 to 2, y from negative square root of 4 minus x squared up to positive square root of 4 minus x squared. And then we have 1, and then d sigma, we need to convert that. We need our conversion factor, which is 2 over the square root of 4 minus x squared minus y squared times dy dx. So there's our little bit of area in the shadow. You multiply it by this conversion factor, it gives you the correct area on the surface, and then you're summing up all along there those areas on the surface to get the total area. Now this particular integral, now we're just back to a double integral, right? And this particular integral can be converted to an integral in polar pretty easily. So now we're back to just changing some double integral into an integral in polar. In polar, you could set up this circle of radius 2 by just letting theta go from 0 to 2 pi and r going from 0 out to 2. And then you would have 2 times the square root, x squared plus y squared is r squared, so this is the square root of 4 minus r squared. And then the conversion factor to convert Cartesian to polar is r, dr d theta. Okay, we're almost there. All we have to do is make a little substitution. Let's let u be 4 minus r squared. Then du is negative 2r dr. And so we get now the integral. Our integral becomes the integral from 0 to 2 pi. And the integral, let's see, when r is 0, u is 4, and when r is 2, u is 0. So I changed my bounds here because I'm doing a substitution. And then 2r dr, that is negative du. So the 2r dr becomes negative du, because du is negative 2r dr. And then this is over the square root of u, and du, and then d theta. Finally, let's see, this is u to the negative 1/2, so we can find an antiderivative here, which would be 2u to the 1/2 with a negative sign there. And we evaluate that antiderivative between 4 and 0. So we have the integral from 0 to 2 pi of, let's see, when we plug in 0, we get 0. When we plug in 4, the square root of 4 is 2, so we get negative 4, but we're subtracting it, so we get 4 d theta. And this is just 4 times the integral from 0 to 2 pi of d theta, which is just 2 pi. So we get 8 pi for the answer.